3 times. They pump 6.3 litres of blood around the body. 4 babies are born worldwide, and 2 people die. To a human, a single second is not a very long time. And yet, in the entire universe, our planet travels 220 kilometers in orbit around the center of the galaxy. Our Sun loses about 1 million tons of its mass out into space. 4,800 new stars are born in the Milky Way, and across the observable cosmos, just under 1,000 supernovae blow entire star systems to smithereens. A lot can happen in 1 second. But is it enough time to build a universe? The smallest fraction of time by which we measure our lives, the second can trace its origins through thousands of years of human history. As early as the 23rd century BC, the ancient Sumerian and Babylonian civilizations devised a system of counting based on the supremely divisible number 60. Later, the Egyptians favored the practicality of the number 12 as the number of finger joints on a single hand that could be counted with the thumb. Our modern concept of time is thus built upon these cultural preferences. Atomic clocks, the universal standard for measuring time on Earth and in space, define a second as 9,192,631,770 radiation pulses of an irradiated cesium-133 atom. As an ultimate definition, it is accurate, precise, but inelegant. It is a reflection of our history, our perception of time, space, and matter. But 1 second seems impractical when considering the history of the cosmos as a whole. Indeed, on a cosmic scale, our universe has clocked up some 436 quadrillion seconds so far. And those seconds can also contain almost incomprehensible vastness. In 2020, scientists in the German electron synchrotron in Hamburg bombarded hydrogen atoms with X-rays, knocking electrons free from their orbits and sending them skipping to the adjoining atom. As the speed of light is the fastest you can go, and hydrogen is the smallest molecule there is, the time it took for this to happen was and is the shortest fraction of time ever measured in an experiment. That time was 247 zeptoseconds, or nearly 250 billionths of a trillionth of a second. There are 2,500 times more zeptoseconds in a single second than there have been seconds in the history of the universe. And so, as we peer back through the eons, glimpsing the universe's childhood from distant and ancient starlight and reconstructing its growing pains in powerful particle accelerators, we uncover a surprising truth. 1 second is more than enough time to build a universe. For most of its existence, our cosmos has looked surprisingly like it does today. Stars have lived and died, galaxies have formed, spun, and collided. Space has calmly expanded and cooled. But our universe did have a beginning, a period of wild revolutionary change, assembling an orderly cosmos from practically nothing at all. Though a single second seems barely long enough to accomplish the ultimate act of creation, as we shall see, the briefest of moments to our human eyes can be an eternity from a different perspective. And incredibly, we can draw a clear line back from our vast present cosmos to the miraculously perfect mix of raw ingredients that came into being in that first moment. So, just how recognizable is our universe when just a single second has passed? Is the cosmos we see and feel around us already inevitable? And with 436 quadrillion seconds to choose from across 13.8 billion years, could it really all come down to the first one? Across the Earth, a cyber attack happens once every 39 seconds. which is once every 39 trillion billion zeptoseconds, or 2,200 times a day. NordVPN has been kind enough to sponsor this video, and they are a premium choice to help maintain a wall around your data. A VPN is like a tunnel that keeps your data private and protected. Whether you're out and about in a coffee shop or at home, Nord is also the fastest VPN there is and has over 5,400 servers in 60 countries. Especially useful if you want to buy discounted games in different countries or access international Netflix or HBO. For example, I was able to watch the recent Matrix film, even though it wasn't available in Spain, where I live. It wasn't great, but I was able to find Cosmos too, which was fantastic. So, to help support History of the Universe and try out Nord with a 30 days money-back guarantee, head over to nordvpn.com/HOTU. Thanks. This is the United States National Radio Quiet Zone. This 34,000 square kilometer patch of land stretches across 3 states and 2 mountain ranges in the eastern US, and demarcates a region of eerie silence from radio transmission, Wi-Fi signal, and cell phone service. And the Green Bank Observatory in West Virginia sits at the heart of this oasis of calm. The exclusion of all earthly sources of radio noise makes Green Bank the best place in the world to listen closely to the stars. And for the last 65 years, the site has been associated with the headline-grabbing search for extraterrestrial intelligence. And in 2012, the immense steerable radio telescope detected a signal that made astronomers sit up and take notice. Coming from a point more than 4,500 light-years away in the Giraffe constellation, a high-speed pulsing signal pierced the West Virginian radio silence. It was loud and persistent, but it was not aliens. The signal was in fact coming from a rapidly spinning and incredibly dense ball of stuff. It was a neutron star, whirling around its axis 346 times a second, emitting a stream of radio noise that intersected with Earth and the Green Bank telescope over and over again. Astronomers named it, poetically, PSR J0740. The star weighed in at around 2.1 times the mass of our Sun, but all of that mass was crammed into a ball that was just 27 kilometers in diameter, making PSR J0740 the most massive neutron star ever discovered, constructed from the densest material in the universe. A neutron star is the corpse left behind when a gigantic star reaches the end of its life. When the heat from fusion is no longer enough to keep the star inflated, the core collapses under immense gravitational forces. In the hydrogen and helium atoms left over in that core, the pressure is enough to squeeze electrons and protons together on a subatomic level, creating a formless paste of neutrons with no empty space between them, weighing 10 trillion kilograms per cubic centimeter. A single spoonful of neutron star would weigh as much as 8,500 Great Pyramids of Giza. But the upper bounds on neutron star densities are still unexplored. Such high gravitational pressures are impossible to replicate in a lab on Earth, but indirect measures and theoretical models can give us an idea. Gravitational waves radiating out from huge space-time distortions are the echoes of catastrophic events too distant in time or space for us to observe. From these, we have found evidence for colliding neutron stars up to 2.2 times the mass of our Sun. And at much higher masses, around 3 times the mass of our Sun, a collapsing star core won't form a neutron star at all, but will rather compress into a black hole. Their impossibly dense interiors are forever beyond the reach of our instruments, and so their formation and structure remain a mystery. For now. In this way, probing the densest objects in the universe mirrors the challenges of probing the formation of the universe itself. As we push the limits in size, mass, and density, our tools and models become increasingly inadequate at describing the bizarre conditions and phenomena. scholars are forced to construct a theoretical house of cards based first on what we do know, then what we think we know, and finally, what seems, statistically, most probable. The further we push into the hearts of neutron stars or reach back into the earliest moments of the cosmos, the taller and more precarious that delicate construction becomes. Mathematics is built upon mathematics, and at any point a single observation or flaw in logic could bring the whole house tumbling down. And so, the universe began 436 quadrillion seconds ago, with a bang. Or perhaps it didn't. It certainly began, but the nature of that beginning is still a subject of debate, to put it mildly. Did the cosmos germinate explosively from the seed of a singularity, or bounce from a preceding universe with a brutal crunch, leaving whatever came before our time and space forever out of reach? Or was it born in a hypothetical multidimensional hyperspace, our precious universe little more than a collision of lower dimensional membranes, impossible to discern due to our limited perception of cosmological geometry? At the very beginning, at the top of the theoretical house of cards, all possibilities are equally bizarre. Fortunately, from this intangible moment onwards, things can only improve. Although it will be some time yet before our universe looks or behaves how we might expect, it is at least a tangible, three-dimensional entity. The arrow of time has begun its flight as the unstoppable march of entropy takes hold. Dividing the smallest distance in nature, the Planck length, by the fastest speed known, the speed of light, you arrive at Planck time. The smallest possible fraction of time in our universe is a septillionth of a zeptosecond, and when a single Planck time has passed, the universe is very, very strange. The entire cosmos is just a Planck length long. Time is undefined and space is ultimately compactified. At this minuscule quantum scale, weirdness rules. Space-time itself is folded and meshed into itself. In this state, which has been described as a quantum foam, microcosmos spanning wormholes and primordial black holes spontaneously appear and disappear without any apparent cause and effect. It is impossible to pinpoint what this Planck-era universe really looked like, as statistically, it is the average of all possible geometries. Nothing makes sense, or even gives a clue to how things might change. But things do change. The primordial heat and energy of the newborn cosmos begin to drop, and for about a quadrillionth of a zeptosecond, the mysterious force of gravity is now manifest in a way that we can understand it. But there is still no matter in the universe, only knotted and tangled energy fields which, for now, are indistinguishable. Today, the strong, weak and electromagnetic forces rule our lives, and the interactions of all matter in the cosmos, but during this so-called grand unification epoch, they are combined into a single, unified electronuclear force. We cannot say for certain how such a consolidated cosmos might have looked, but without anything for it to yet act upon, the question is perhaps immaterial. Cooling continues, and the strong nuclear force is the first to break free from its brethren. The sudden split is enough to spawn a new generation of stuff in the universe, as the messengers of the new strong force, gluons, spring into existence, alongside something entirely new, the first particles of true matter. But the emergence of the strong force also triggers another event, one which will come to shape the universe and our experience of it. Suddenly, after 10 quadrillionths of a zeptosecond of existence, the cosmos inflates. It grows at a spectacular, exponential rate, doubling in size more than 90 times in 100 billionth of a second. In a flash, the universe increases its volume by a factor of 10 to the power of 78. The random quantum fluctuations that ruled in the Planck-sized universe were suddenly inflated to tangible size, freezing energy variations in place that would come to define the large-scale structure of the cosmos. But at the same time, space expanded so much, so fast, that the local confines of our observable universe were set, and would forever exclude distant, potentially exotic parts of the cosmos as a whole. With inflation completed a trillionth of a zeptosecond after it began, the new, larger and matter-filled universe continues to expand, but at a more stately pace. Gluons of the strong force intermingle with matter and antimatter particles that arise spontaneously from photons. Many of these pairs are destined for destruction, however, annihilating together to turn back into photons. In this way, the universe is yet to decide exactly what it will be filled with, and it is too hot for anything to stick around for long. Expansion continues. A single zeptosecond ticks by, and then another, and then a billion more. Finally, the temperature and energy of the universe drops enough for the electroweak force to split. Like a spinning coin on a table, with one side indistinguishable from the other, it slows and eventually settles, with heads and tails distinct. The electromagnetic force and weak nuclear force as we know them today become distinct. More varied particles begin to emerge. We enter an age of matter over energy, and the material seeds of our universe are sown. The universe is still much hotter and much more energetic than it is today, but it has finally reached a level that is within the realms of our most powerful instruments. Using vast particle accelerators, we can simulate the conditions of the universe a billion zeptoseconds in. We have reached the lower stories of our theoretical house of cards, and we can begin to say with certainty how the hot cosmic soup behaved. Through those billion or so zeptoseconds of the early universe, only the smallest fundamental particles could hold their shape, and even then, not for long. In a cooler cosmos, gluons have the power to combine triplets of quarks together to form protons and neutrons. But at this early time, although both quarks and gluons exist, it is still too hot for them to unite. So, free quarks and antiquarks spring into existence, float around freely for a while, and then collide and obliterate one another in a shower of photons again. As temperatures drop, leptons like electrons and positrons also enter the fray, but it will be a long time before they settle down. A few more trillion zeptoseconds pass and the expanding cosmos cools. Fewer spontaneous particle births take place, and gluons can finally combine quarks into larger, composite hadrons, bringing many of the antimatter collisions and annihilations to an end. Depending on the quark ingredients, the gluons help to build protons, neutrons, and other more exotic hadrons, along with their antimatter counterparts. And so, after a billion trillion zeptoseconds, a single second has passed. The cosmos is filled with matter, the raw building blocks of everything we see today. Our observable universe is now about 20 light-years across. The entire cosmos is as similar to the heart of a neutron star as it will ever be. It is hot, super dense, and filled with hyper-compressed matter quite unlike anything we see elsewhere or have seen since. For the neutron star, there is no going back. The simplicity of its interior leaves no room for escape from the crushing gravity and the gradual, interminable cooling. But the universe, after 1 second, is full of potential. All the matter and energy and fields and particles that will create the cosmos we see today. For the second-old cosmos, the sky's the limit. But there are many ways to build a universe. The events that take place as the first second ticks by will prove to be pivotal to the way our cosmos evolves. Despite the bounty of its frantic first zeptoseconds and the many quadrillion seconds still to come, the universe's destiny is in the hands of physics at this very moment. Just how differently could things have turned out? On April Fool's Day, 1948, the scientific journal Physical Review published a paper that would end up making history for the wrong reasons. PhD student Ralph Alpha had spent the last year developing his ideas for how the universe's chemical elements came to be, along with his supervisor George Gamow at the Johns Hopkins University in Maryland. But as the paper was finalized, Gamow spontaneously invited the eminent physics professor Hans Bethe to co-author the finished paper, even though he'd not contributed to the work at all. The sole purpose of this mysterious move was to complete a Greek alphabet author list, and alpha, beta, and gamma's origin of chemical elements became known as the Alpha Beta Gamma paper, or more simply, the alphabetical article. Alpha, perhaps justifiably, was not amused. Beta had been happy to add his input to further discussions, but when the theory foundered in the face of new data, he reportedly considered changing his name to Zacharias. Alpha's hijacked theory was a relatively simple one. He supposed that all of the chemical elements that are in existence today were assembled in the earliest moments of the universe through the successive capture of neutrons, making larger and larger atomic nuclei. His calculations showed how the increasing energy needed to make each element could account for the modern-day abundances of the elements, namely that the lighter atoms are much more numerous than their heavier cousins. It was a reasonable theory for the time, and the maths held up. But a problem soon emerged. Out of all the elements that have been discovered and documented, none of them have an atomic mass of 5 or 8. There is helium with a mass of 4, lithium with a mass of 7, and beryllium with a mass of 9. But nothing in between. These missing masses posed a big problem for Alpha's stepwise elemental assembly. You can't climb a staircase one step at a time if 2 of the steps are missing. So there must be another explanation. In trying to understand how our modern universe was made, it first helps to know what the universe is made of. There are 92 elements that occur naturally on Earth, each with a unique number of protons in their atomic nuclei, and some with slightly variable numbers of neutrons, giving rise to various isotopes of varying long-term stability. The smallest and simplest is hydrogen, comprising just a single proton, while the heaviest is uranium-238 with 92 protons and 146 neutrons. Looking beyond Earth, astronomers and planetary scientists have spent centuries examining the compositions of the moons, other solar system planets, meteorites, our sun, other stars in our galaxies, and the exoplanets that orbit them, gas clouds and nebulae, as well as distant galaxies and intergalactic dust. Their goal is to establish what they are made of, and by extension, what comprises the universe as a whole. And the ultimate conclusion, bolstered by new discoveries every day, is that the basic ingredients are the same. There are only these 92 naturally occurring elements wherever we look. But there is plenty of variation in how these elements are distributed. On a relatively local scale, our Sun hogs much of the hydrogen and helium in the solar system, although plenty of hydrogen is also to be found in icy water around the system's outer edges and in the gas giants that lurk in the shadows. Heavier elements tend to collect closer to the star, providing the building blocks for solid rocky planets, like Earth, Venus, and Mars. But there are also patterns to be found on a galactic scale. The closer an interstellar traveler strays to the center of the galaxy, the more of the heavier elements they will encounter. And if they should visit a long-lived star, like a cool-burning red dwarf, they would notice a relative paucity of heavier elements, with a corresponding lack of rocky planets in orbit around them. Piecing together the clues in these galactic patterns, it becomes clear that the abundances of the elements are intrinsically linked to the births and deaths of stars. In the center of the galaxy, where gravitational forces are most intense, matter is churned into a turbulent, dense mass, constantly warped and twisted into collapsing knots. Stars are crushed into existence as fusion ignites bright points of light that burn hot and fast before dying spectacularly and seeding the roiling clouds once again. Here, stars live fast and die young, recycling their fuel time and time again over several billion years. In contrast, long-lived red dwarfs burn slow and cool, often in the outer, calmer reaches of the galaxy. Born long before frantic stellar living and dying took place, their compositions are an invaluable window into what things were like in the galaxy's earlier years. Drawing conclusions from this stellar testimony, we see that the heavier elements owe their existence not to a gradual neutron assembly at the beginning of time, as Ralph Alpha posited, but rather to the ongoing processes inside stars. And ironically, it was Hans Bethe who continued this train of thought throughout the 1950s and 1960s, building on the parallel research into nuclear fusion to consider the energy sources inside stars. He spent these decades devising mathematical models to describe how most of the heavy elements could be assembled in their hot, dense cores, from the simple building blocks of hydrogen and helium. This process of stellar nucleosynthesis proved robust even after some 50 years of advancing astronomy, and in 1967, Hans Bethe, the cuckoo in the alphabetical article nest, was alone awarded the Nobel Prize in Physics for his theories. Stellar nucleosynthesis sees everything from lithium to uranium forged in the hearts of stars, or during their inevitable catastrophic destruction. But what it doesn't explain is how the lightest elements, hydrogen and helium, came to be in the first place. And in fact, while the alpha, beta, gamma paper may have been wrong about most of our elements, it may just have been onto something with the lighter ones. The raw ingredients for everything in the universe must have already been in place before the first stars were born, so they must owe their creation to an entirely different process. One that was shaped by the state of the universe in its very first second. In the clear morning light, the bare, windswept summit of Mauna Kea is adorned with a necklace of smooth white domes. Each is a huge observatory housing some of the most important telescopes in the world today, all of which take advantage of the uniquely clear view that the Hawaiian volcano's position affords. The air above Mauna Kea is exceptionally dry, allowing astronomers to see stars, galaxies and nebulae with better precision than almost anywhere else on Earth. Scientists squabble and scramble for invaluable time with one of the 13 telescopes that crown the volcanic massif, each hoping to find the answers to their own cosmic mysteries in the crisp Hawaiian sky. So it was that in 2013, 3 American astronomers used the powerful 10-meter-wide Keck telescope to discover something surprising. With the telescope pointed towards the constellation of Leo, they had been searching for quasars. These bright, star-like objects are thought to be extremely luminous galaxies that were common during the universe's first billion years or so. But before they could find what they were looking for, the astronomers spotted something else, something which was blocking their view. A cloud of gas, too dim to be visible to the naked eye but easily spotted by the powerful Keck, and by measuring how much the cloud's faint light had been stretched and redshifted by the expansion of space, they calculated that it lay some 11.6 billion light-years away from the Earth. Of course, the further we peer into the distant reaches of space, the further back in time we can see. In addition to probing the atmospheres of exoplanets, the new James Webb Telescope will also turn its instruments to the farthest light it can possibly find. And so, the light from these distant clouds had travelled 11.6 billion light-years, meaning that it must have departed 11.6 billion years ago, when the universe was a little under 2 billion years old. We have seen stars and galaxies at this distance dating from this time, so we know that the universe's age of starlight was in full swing. But when the astronomers scanned the cloud to determine its composition, they found a puzzling simplicity. These clouds contained only hydrogen and helium. Gas clouds are no great novelty in the universe as a whole. They are scattered within and between galaxies and contain within them the scattered remnants of long-dead stars. The fusion within these stars creates heavier elements of carbon, oxygen, even iron, and when they die, they seed the space around them with the ingredients for making new stars, as well as the rocky planets and moons that come to orbit them. But these mysterious new clouds contained none of that. To remain uncontaminated by anything heavier than a helium atom, they must have never witnessed the birth and death of stars, never been ignited by stellar fusion. It was then the astronomers realized that they were, in fact, pristine relics of the universe as it was just 1 second after the Big Bang. When all around them had been pushed and pulled, chemically reforged and redistributed, these tiny patches of space had managed to escape. Today, as their light reaches the magnificent Keck telescope on the summit of Mauna Kea, they help to paint a picture of the universe when it was just 1 second old. From an unimaginably hot, indistinct and energetic soup, the second-old universe is now a moderate 10 billion degrees and measures several light-years across. It is filled with the victors of particle battles, along with the photon shrapnel of countless mutually destructive encounters. Those particles which possess mass today are already endowed with it thanks to the Higgs field. The 4 fundamental forces, strong, weak, electromagnetic and gravity, are in full and comprehensible operation, although their behavior in this hot and energetic firmament is quite different to today. And it was, in this moment, about 1 arbitrary human second in, something happened that would set the stage for all that was to come. Something that would lead directly to the creation of hydrogen and helium clouds like the ones spotted from the summit of Mauna Kea, and would indirectly come to shape the evolution of the entire cosmos. In August 1868, the Indian town of Guntur, near the country's eastern coast, swelters under the growing heat of the morning sun. French astronomer Pierre Janssen sweats beneath his wide-brimmed hat as he fusses about his instrument, watched at a respectful distance by a crowd of curious locals. Adults and children alike peer along the instrument's heading, wondering what the scholar could possibly hope to gain from pointing his telescope directly at the blazing sun. They consider the very real possibility that the sweating Frenchman is quite mad. But Janssen is not mad. Indeed, he has travelled for a month, covering nearly 6,000 miles from his home in Paris, specifically to be in this very position at this very moment. Shading his eyes, he risks a quick glance at the sun and sees with satisfaction a tiny nibble into its edge. For Janssen is a 19th century eclipse chaser, and the main event has just begun. As the shadow of the moon creeps across the face of the sun, the late morning air becomes noticeably and eerily cooler. Cows moo in the pastures, and birds dart restlessly from tree to tree. The animals are unsettled, but Janssen is in his element. With a final tweak, the telescope and its accompanying spectroscope is in place, just in time for the moment of totality. Day turns to night, and in the sky above a ring of bright light is all that's left of the scorching star's light. The sun's corona projects past the moon's shadow, and Janssen, now cool, calm and collected, makes quick and accurate notes of what his spectroscope reveals. Spectroscopy was relatively new to science at the time of Janssen's expedition, but had already proved a valuable tool for identifying specific chemical compounds in any emitted light. Chemicals emit or absorb very specific wavelengths of light, so in a complete spectrum they leave behind a fingerprint of lines particular to that compound. Spectroscopy is such a powerful tool, in fact, that it is still being used in some of the most advanced astronomical probes today. Indeed, the James Webb Space Telescope will search the atmospheres of exoplanets with its spectroscope, looking for fingerprints characteristic of lifelike gases, like oxygen and methane. Janssen is already familiar with the spectral fingerprint of many of the compounds on Earth. Sodium, hydrogen, and many more have already been studied in depth. But during this eclipse in India, the astronomer feels a flush of excitement as he sees a pattern that he has never seen before. A bright line, close to the fingerprint for sodium, but different enough to merit its own classification. It doesn't match the spectrum of any known element, and so, he concludes, it must represent something new, lurking out there in the sun's corona. The line is bright enough that it could be seen even after the moon's shadow passes, and Janssen's observations are confirmed by English astronomers just a couple of days later. They name this new, abundant, alien element helium, after the Greek word for the sun. If helium was indeed a new element, then its method of discovery was very irregular, and many other scientists were skeptical. How likely was it, really, that an element could be so abundant out there in space, and yet have evaded detection on Earth? Today, helium is best known for its use in party balloons, but it has also become an invaluable part of our modern lives. The inert gas is lighter than air and has an exceptionally low boiling point, making it essential to high-tech industry and medical science. This is because, fortunately, in the early days of the 20th century, prospectors in oil fields around Dexter, Kansas, struck gaseous gold when they found the unreactive element mixed in among the more expected natural gas reserves. It transpired that the same geological wrinkles that work to trap oil and methane beneath the surface also captured helium. But even this federal reserve is finite. To date, every source of helium on Earth has been found by accident, and those sources are beginning to run dry. We consume 140 billion litres of helium every year, and with no easy way to find more when we run out. Unless it is trapped by geological flukes, most of Earth's helium simply floats out to space, which explains why it was so difficult to detect here in the first place. The gas's paucity on Earth is made all the more painful by its spectacular abundance in space. Helium is the second most abundant element in the entire universe, making up around 25% of all the atoms in existence today, and second only to that of hydrogen. And remarkably, scientists believe these cosmic abundances were baked into the universe some 13.8 billion years ago, when the cosmos was just 1 second old. It is these abundances that drove the creation of stars, planets, and life, and if it weren't for a seemingly insignificant quirk of particle physics, then solar systems, galaxies, and the entire universe could have followed a very different path. After 1 trillion billion zeptoseconds or 1 full second, the cosmos has been filled with matter. But that matter is still behaving strangely. Protons and neutrons have been created by the binding of quarks. But in this hot particle soup, the hyperactive weak force nudges the hadrons to switch identities, with a helping hand from free-floating electrons and positrons. Protons become neutrons, and neutrons become protons. And while the temperature is sufficiently high, the reactions balance each other out, so there are approximately equal numbers of each. But at 1 second, the temperature of the cosmos drops far enough for the weak force to lose its potency. The identity-switching reactions slow down and eventually stop, in a process known dramatically as freeze-out. But the universe at this point is by no means cold. It is still 10 billion degrees on average. For particle physics, though, this is cold enough, and the final hadron switches take place, fixing the numbers of protons and neutrons for the rest of time. It is well known that protons and neutrons differ in their overall charge. Protons are positively charged, while neutrons carry no charge at all. But less famous is their minuscule differences in mass. Neutrons are about 0.1% heavier than protons, a difference that is scarcely noteworthy in modern-day chemistry, but which proves fundamental to shaping the cosmos 1 second after the Big Bang. The Greek myth of Sisyphus tells us that it is far easier for a rock to roll downhill than it is to push it back to the top. And in our universe, every phenomenon seeks the lowest possible energy level, so reactions that reduce and release their energy will always be favored over those that need energy input. Thus, in the identity switch between protons and neutrons, the reaction would tend to fall in the easiest direction, from heavier particle to lighter one, from neutron to proton. As the free energy of the universe drops, there is less opportunity to push things back in the other direction, and the hadron equilibrium shifts in favor of the proton. By the time the freeze-out is complete, protons outnumber neutrons 6 to 1. And even after the freeze-out, the heavier, energy-rich neutrons are still not safe. Lightweight protons on their own are stable, but isolated neutrons will spontaneously decay back into proton and electron after just 15 minutes or so. Had things continued this way, there would be no neutrons left in the cosmos today. Fortunately for us, this was not their fate. Many neutrons found refuge from impending doom by the simple act of binding with a proton. Combined with its lighter kin, they could hold decay at bay indefinitely, and in doing so formed the very first composite atomic nuclei. One proton and one neutron locked together by the same gluons that hold together their constituent quarks. The result is the nucleus of so-called heavy hydrogen, deuterium. Before long, much of the deuterium is paired together too, to make what we recognize today as helium. And therefore, the helium we find today is both the safe haven and protective prison for every neutron left adrift after the cosmic freeze-out. Its abundance in the universe was ultimately set by the balance of protons and neutrons, which owes its tilt to the tiniest of mass differences between the tiniest of fundamental particles. Scientists don't know why the scales fell in that particular direction. They have no good explanation for why the proton should be intrinsically lighter than its uncharged sibling. It seems to be one of those universal phenomena that just is, set by a roll of the dice when the first fundamental matter emerged. Things potentially could have just as easily fallen differently, with protons very slightly outweighing neutrons instead of the other way round. The difference may be trivial, but the consequences are astounding. If protons were the heavier sibling, then neutrons would have outnumbered them at the end of the 1-second freeze-out. Left alone, the proton would decay back into a neutron, although some could be saved by combining with a neutron, forming, as we saw in our reality, a helium nucleus. But helium is famously inert. The real fuel for the cosmos is hydrogen, whose nucleus consists of a single proton. In an alternate reality where protons were heavier and more unstable, none could persist long enough to form hydrogen. Unbound neutrons would be stable, but being uncharged, there is no hydrogen equivalent they could form. After 1 second, the universe would be filled with only unreactive neutrons and unreactive helium. With only these ingredients, it is hard to see how a universe like ours could possibly evolve. No stellar fusion, no stars, no supernovae seeding the cosmos with heavier elements, no planets, no water, no organic life, no us. It would be a poor, cold, and barren universe with helium alone. So, we may bemoan the paucity of helium on Earth and stare longingly at its richness in the universe, but there can be too much of a good thing. The chance conditions that shape the cosmological freeze-out seemed, like so many of our universe's starting points, to be tuned just right. The tiniest, inexplicable mass difference having the capacity to create complex, sentient life. Or to create nothing at all. Scientists and philosophers are still trying to understand how we ended up so lucky, but the simple fact may be that our universe is a statistical fluke. Roll the dice enough times and you will happen upon the result you need, eventually. The rest, the failed attempts, produce barren, alternate universes in a vast, possible multiverse where no stars could shine and no life could evolve to contemplate its unlucky fate. And so, 1 second after the Big Bang, there is huge potential in our nascent material universe. Protons and neutrons form hydrogen and helium nuclei in a proportion determined by the tiniest inexplicable mass difference, and in doing so mark the beginning of a much more standard and understandable cosmology. Most of these primordial elements will find themselves pulled together into stars, crushed and fused into heavier elements, and exploded back out. Each primordial hadron is reconfigured and reused time and time again, building stars, planets, and eventually, us. Our cosmos will evolve along a path that has been laid by events during this first, fleeting eon. A few small pockets, however, escape this fate. Their light reaches us as the relic clouds near the constellation of Leo. From the summit of Mauna Kea, we can catch a glimpse of a small window on the cosmos, not only 2 billion years after its creation, but also stretching back to that very first second when the ingredients to make a universe were already in place. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.